All right, this is it. This is the last lesson for chapter 3 of Algebra 2. We're going to be talking about inverse matrices and how to solve systems with it. So, we're going to do a little bit of vocabulary, kind of like we did in the last lesson and all of those things. And we're going to start, I know we're doing inverses, but we can't really talk about inverses without talking about the identity matrix. Now, so the identity matrix and then the inverse of a matrix really they connect directly back into those words when we're talking about just like additive identity or multiplicative identity, all those kind of things. So, what an identity matrix? Now, we're going to be using only 2x2 matrices, pretty much in this lesson, but identity matrix can be any size square matrix. That's important. So, what an identity 2x2 matrix looks like is it looks like this right here. 1, 0, and 0, 1. That's the identity matrix right there. Diagonal, one's going down, zeros everywhere else. And just to kind of put the point home, again, we're really not going to be talking about 3x3s or 4x4s or anything like that in this lesson, but to get the point home of what an identity matrix looks like, it looks like this. So this is a 3x3, 1, 0, 0, and then 0, 1, 0, and then 0, 0, 1. So see, it's got ones all along this sort of main diagonal going down, and then zeros everywhere else. So that's what an identity matrix looks like. So what does that have to do with inverses? So, craziness. Definition of an inverse matrix. So an inverse matrix, so if we have a matrix A, its inverse, and we do that symbol with this like that. So it's like a to the -1, but it's not actually to the -1. It's kind of like inverse sine and cosine if you saw that in geometry or whatever else. Where in this context, in the context of matrices, this means inverse, not exponent, right? And so an inverse of A is in order to be it, for this to be the inverse, if we take and we multiply A times the inverse of A, we get the identity matrix. So if you take a matrix and multiply it times another matrix and you get the identity matrix, then these two are inverses. So I'm going to kind of write in like some words. So this would be matrix A. This would be the inverse of A. Inverse of A. And this would be the identity matrix. Now, it's the identity matrix that's the same size as whatever A is. So if A was a 2x2, then it would be a 2x2 identity, 3x3, etc., right? So the identity. So that's what an inverse matrix is. It's a matrix that cancels out another matrix, which is going to be really important for when we get to the end of this, and that's how to solve systems with it. So it cancels it out, and canceling out, so when we cancel out addition, we get 0. Like the inverse of 5 is -5, right? The additive inverse, because it gives us 0. But for multiplication, the canceling of the thing is 1, right? So if the multiplicative inverse of 5 is 1 over 5, because these two gives us 1. And so just like that, and that just like what canceling it out means different things if we're talking about addition, subtraction, or multiplication, division. It's the same idea here. If you cancel out a matrix in this context, you get the identity matrix. You get whatever the identity of the thing is. That's true here, because the additive identity is 0. The multiplicative identity is 1, right? And so inverses and identities are completely linked in concept, right? So let's start out by doing some examples and testing to see if some matrices are inverses. And so if they are in fact inverses, and this has to be able to go both ways, and we'll see this in a second. If you have to be able to do, like, if A times B is the identity, but B times A is not the identity, then these are not inverses, right? So it has to go both directions. Because remember, when we're multiplying matrices, the direction, the order matters, right? And so it has to work both ways for it to be the identity. So in order to test if A and B are inverses, you just have to multiply them. And if either one going either way doesn't give us the identity, then we don't have the answer. So you notice there's fractions. That's the one thing that's a little bit scary about inverse matrices is we very often end up with fractions. You'll see kind of why when I show you how to find the identity, the inverse of a matrix here in a minute. So let's do this example. So we're going to start by taking this and we're going to multiply A times B. So A times B. Ooh. This one, since I've already written it, I'm not going to rewrite the matrices. I'm just going to kind of do it. So -4 times 1/4 is -1. Oh. And then 2 times 2, excuse me, 2 times 1/2 is 1. So -1 plus 1 is 0. So I don't actually even have to go any further than that because this first spot has to be 1. So I actually don't even have to do anymore. So I don't even have to test B times A because if either one of them aren't the identity, then this one isn't the identity, right? So this one, so these are not inverses. Not inverses. Okay. So what about these two? So let's go through and multiply here. So this one, so F times G equals, so 3 times 3/4, that's a little more complicated. That's 9/4, right? So we've got 9/4 plus -5 times 1/4 is -5/4. So plus -5/4. Let's go ahead and kind of start checking as we go. Because like we saw with this pink one over here, sometimes we can just quit, right? So 9/4 plus 5/4 is 4/4, which is 1. So it's looking okay so far, right? So let's do the next one. So we've done sort of this and this. We've got to do this and that next, right? So this and this next. So 3 times 5/8 is 15/8. So 15/8 plus -5 times 3/8 is -15/8. So -15/8. So 15/8 plus -15/8. This one's 0. We're still looking pretty good. You can see where we're going to go, but let's walk it all out to make sure we get what's going on. So so we've done all of the first one, so we're going to go down to the next row. So -2 times 3/4 is negative. That reduces some, so -3/2. 3/2. And then 6 times 1/4 is 3/2. So plus 3/2. So that turns into a 0. And then this next one, -2 times 5/8 would be -5/4. 5/4. And then 6 times 3/8 would be 3/4 times 3 is, I'm having trouble hitting this in my head. So 6 over 1 times 3 over 8. This turns into 3. This turns into 4. And 3 times 3 is 9. 9/4. Oh, yeah. Yeah, it's great. I thought it wasn't working, but it is working. Plus 9/4, which is 1 as well. So that works, but before we can say for sure that F and G are inverses, we got to try it the other way. So let's do that. So G times F equals. This time I am going to rewrite these so that I can keep the order straight. So this is going to be, actually, I'll just go ahead and do it here. So G is 3/4, 5/8, 1/4. So I don't have to do this. I'm rewriting this one so that I don't have to do it backwards because that sounds like a recipe for disaster. Right? And then we're doing that times f, which is 3, -5, -2, and 6. Okay, so now 3/4 times 3 is 9/4. See what's happening here, right? So 9/4. 5/8 times 2 is 10, no, 5. 5/4, -5/4. So plus -5/4. So that is 9/4 plus -5/4 is 1. So that works. So 3/4 times -5 is -15/4. 15/4. And then 5/8 times 6 would be 15/4. So plus 15/4. Those two go to 0. Also looking good. Let's do this next one. 1/4 times 3 is 3/4. 3/8 times 2 is negative. So plus negative 3/4. Which turns into 0. Great. Happy days. And then 1/4 times 5 is -5/4. 3/8 times 6 is 9/4. So plus 9/4, which is 1. So these, in fact, are inverses. Let's just do a smiley face. Sound good? They are inverses. All right, so what next? Here we go. So this is how to test if two matrices are inverses, which is helpful. It's less helpful for kind of the end goal of this lesson, but it's kind of helpful in kind of walking through all the bits and understanding what's going on and all of those things. So if we're given a matrix A, how do we find its inverse? Okay, so this is how to do it. If we have an inverse A, and we're gonna do this, and this is specifically with a 2x2. So what we do is inverse of A, and A is this matrix. A, B, C, D. Oops. Oh, D. Right? Okay, so this is how to find the inverse of A. So inverse of A is 1 over, and I'll expand this out in a minute because we usually write this out this way. 1 over the determinant of A, right? So these two multiplied minus those two, right? We'll write all this out in a second. Times, and this is a little bit tricky, but it's just something you're gonna have to memorize. We're gonna flip stuff. We're gonna flip stuff along the diagonals, and you just gotta kind of remember the pattern. And what we're gonna do is we have these two change places, and these two change signs. Okay, so let me write that out. So that's going to turn into D right here and A right here. So these two switch places, and these two switch signs. So negative C and negative B. Right? So let's write this fully out with the determinant all written out. That way we kind of have a full sort of formula, I guess. I don't know why I wrote the A like that. Just kind of did. Happened. All right. So 1 over. Now to find the determinant of A, we do A to... Whoa, hiccups. I don't know how I feel about that. A times D minus C times B. So that times this matrix. And again, we're flipping the direction of the down diagonal. So D and A, and then flipping the sign of the up diagonal. C and negative B, or the opposite of them if you prefer that wording. Probably is a better wording, I suspect. So yeah, so let's actually do that. Let's find one. Let's find the, oh my goodness. I don't know why it does that sometimes, or maybe, I don't know. I don't know what I'm doing. So we're going to find the inverse of this. So let's start out by finding the determinant of this one. So the determinant of this guy, let's go ahead and write this all the way out. So 7, -5, 2, -1, right? So find the determinant. So 7 times -1 is -7. And then we're going to do minus the up diagonal. So minus 2 times -5, which is -10. And then that gives us, we've got to ka-chink these right there. So -7 plus 10 is 3. So there's the determinant. So find the inverse. We do 1 over the determinant. So 1 over 3 times, and this is just, I maybe should have said this, but this is just scalar multiplication. So just multiplying this times everything. So we're going to take and flip the order here. So this is going to be -1. And then 7 is going to be down here, and then flip the signs of these. So this is going to be -2, and this is going to be +5, right? So then we just multiply it. So that equals -1/3, 5/3, -2/3, 7/3. See if anything reduces? Nothing does. That's the answer. That's not such a big deal. It's fractions, but usually the fractions on these are pretty easy. And so it's kind of a fun way to do things. So let's see what we can do here. Now, so this is where we get to the punchline, get to the finish on this deal. So how can we use inverses to solve a matrix? So let's kind of show an example that is just regular algebra without matrices. So if I have A times X equals B, and I want to find X and solve for X, what do? Well, I can get rid of this A. This A is multiplied on here, so I need to multiply to get rid of it. So I need to multiply by its inverse. So in this case, I would multiply times the multiplicative inverse, so 1 over A. And I would do that, I don't know why I wrote 8. 1 over A. And I would do that on both sides. And I'm doing it in front here because, matrices is going to matter. And so that's going to cancel, and that would just give us X equals the inverse of A times B. Well, it turns out that you can do the same thing with matrices. So I'm going to kind of write something kind of generic here, and then we're going to use this to actually solve a system. So if I have an equation that looks more like this, where I have matrix A times matrix X equals matrix B, how would I get rid of this matrix A? Well, I would multiply times its inverse. So I would multiply both sides by the inverse of A, times the inverse of A and times the inverse of A. I don't know why I wrote it that way. Let's do it in the front. Times the, I'm tired today, y'all. Should have slept more last night. Times the inverse of A and times the inverse of A. So let's rewrite that real pretty, and then we'll see how this goes with the system here in a second. So X would equal the inverse of A times B, right? Now, let's put some bones on this flesh, or flesh on this bones, and use that to solve this matrix. So So we've got a system here, and we're asked to solve this using inverse matrices. Now, why don't we use substitution or elimination? Because we don't. Because we're learning a new method. Get over it. It'll be fine. You'll live. You'll live. I promise. So first of all, we need to turn this system into a matrix equation. I'm going to show you what the equation will look like, and then we'll see if you can kind of understand what's happening, and then I'll explain what's happening. So we can turn this system, we can rewrite this with matrices if we rewrite it like this. So it'll look like this. It's going to be 1, 2, 3, -6 times the matrix, the 2-by-1 matrix that has X and Y in it. And that equals the solution matrix. which is going to have 9 and 3 in it. So see what we did here? And actually, if you multiplied these two matrices out, you would actually get this whole thing. 1 times x is x, and then plus 2 times y, right? Follow me if that's for the first thing. So we get a matrix with all of that in it. So, but all we did was took the coefficients. The only tricky one here is that if there's nothing there, there's an implied 1, right? So that's taking this regular matrix and turning it into, excuse me, I keep saying that, this regular system and turning it into a matrix equation, right? And so that's setting our stage to do all of this. So now how can we use this to solve for x and y? So it would be taking, and we would be solving for this matrix right here by taking the inverse of this matrix and multiplying it times this one right here. Okay, so let's start by finding the inverse of this matrix. So let's find the determinant of that matrix. So the determinant of that, I'm going to write this all the way out. You could probably just kind of go to the like multiplication stuff at the bottom, but just for note's sake, I'm going to make sure I'm going to get this all in here. That way you can remember when you're going back and looking at your notes, what in the world you did to get the thing. So find the determinant of this. 1 times -6 is -6, minus 3 times 2 is 6. So -6 minus 6 is -12, right? Looking good so far. This one doesn't have yet. We'll see. I don't know how pretty our answer is going to be. So that's the determinant. So to find the inverse of this guy, we would take and multiply 1 over -12 times the flippity floppity matrix. I should totally do this in a different color. You probably don't have to erase, but just to keep it all clear that these are kind of different steps, different layers. Struggling. Almost done with this video. 1 over -12 times this thing. Here we go. Flippity flop these. So -6 over here and 1 right there. And then flip the signs here. So -3 and -2. And then we gonna distribute all of this. So -112 times -6 is positive 1/2. -112 times -2 is positive 1/6. -112 times -3 is positive 1/4. And that, of course, is just -1/12. Yeah, looks all good. So now, to find x and y, all we got to do is multiply this times that. Again, the nice thing about doing solving a matrix this way is it's very, very procedural, and it's very much you always do this thing. It's not a try to figure out this and then which one are we going to multiply? What thing are we going to solve for? No, it's just this is how to do it. Do it this way every time. So we're going to multiply that times 9/3. 9/3. The matrix 9, the 2 by 1 matrix 9, 3. All right. So 1/2 times 9 is 9/2, or 4.5, whatever floats your boat. 1/6 times 3 is 1/2. 1/4 times 9 is 9/4. What am I doing? This should have a plus right here. 1/4, yeah. That and then plus 1/2. 9/4 plus -1/6. No. -3/2. I'm telling you. -3/2. It's the simple stuff. Okay, so 9/2 plus 1/2 equals 10/2, which is 5. So x equals 5. Look at that. X equals 5. Now this one's a little more complicated. This would be 9/4 minus 6/4, so 3/4. Positive 3/4. So the answer to this system, and you could do it another way to test it or whatever else, but the answer to this system is the ordered pair 5 3/4. Blam. That's it. That's solving systems with inverses, and that is it for this. That is it for this entire chapter, which is all about systems and matrices and all that kind of stuff. We're going to get into some quadratics in the next one. We shall see you there. If you're one of my students, thanks for joining us. Do your homework. See you in class. If you're not one of my students, thanks for joining us, and let us know how else we can help. Bye-bye.